Steel production starts from ferrous and non-ferrous raw materials, proceeds through reduction of iron ore to metallic iron, refining to remove impurities, casting into semi-finished shapes, and transformation into finished products by rolling and heat surface treatments. The classical integrated route uses ore, coke, and fluxes, while a second route relies almost entirely on scrap, the electric route. Below is the linear procedure from origin to finished product. Begin with raw materials. In the integrated route, you need iron ore, hematite, magnetite, metallurgical coal to make coke, fluxes such as limestone and dolomite, plus some scrap to balance the charge. In the electric route, the base is ferrous scrap, often supplemented with pre-reduced materials, DRI-HBI, made by reducing ore with gases rich in hydrogen and carbon monoxide. Upstream, ore is beneficiated by crushing, screening, magnetic separation, and flotation to raise Fe content and reduce gangue. In the integrated route, metallurgical coal is converted into coke in battery ovens. Coal, in the absence of air, is heated to about 1,100 degrees for 15-20 hours. The result is porous, strong coke, coke oven gas, and byproducts, tar ammonia. Fine ore is agglomerated to improve permeability in the furnace, sintering, sinter, or pelletizing, pellets. Sinter is made by mixing ore fines with coke breeze and fluxes, spreading on a suction grate and igniting the top. Pellets are formed in discs or drums with binders, then indurated in grate kilns. Ore reduction to iron occurs in the blast furnace. The blast furnace is a counter-current reactor. From the top, alternating layers of sinter, pellet, coke, and fluxes are charged. From the bottom, hot blast air at 1,200 degrees C. Sometimes oxygen enriched with injected auxiliary fuels, pulverized coal, oil, gas, is blown in. Coke supplies heat and CO as the reductant. The hot metal is transferred in a torpedo ladle to the basic oxygen converter, BOF-LD. Here, primary decarburization occurs. Scrap, to absorb heat, and hot metal are charged, then high-purity oxygen is blown from above at sonic velocity through a lance. Oxygen oxidizes C, Psi, Mn, and P, with additions of lime and dolomite to capture oxides in the slag. In the electric route, scrap is melted in an electric arc furnace, EAF, by graphite electrodes delivering tens of megawatts. Fluxes and, if needed, DRI-HBI are added. Melting and controlled oxidation remove impurities. Oxygen and carbon injection, foamy slag practice, burners, and injectors improve efficiency and quality. Modern EAFs enable rapid, precise heats and are typically paired with ladle furnaces for downstream refining. After primary steel making, the heat goes to secondary metallurgy in the ladle. Here the composition is finely adjusted, alloying with Min, Psi, Car, Ni, Mo, Nb, Ti, Bv, Al, and inclusions and dissolved gases are refined. Vacuum stations, VD, VOD, remove hydrogen and nitrogen and allow low carbon levels in stainless grades. VOD combines oxygen and vacuum. Bottom argon stirring promotes thermal and chemical homogeneity. Lime flux and synthetic slags clean by absorbing inclusions. Temperature and chemistry are monitored in real time to hit the target grade. Casting converts liquid steel to solid semi-finished forms. Continuous casting is standard. Steel flows from the ladle to a tundish, buffer and filter, under protective powders, then into water-cooled molds. Solidifying from the shell inward, the strand is withdrawn and cut into slabs for plate and coils, blooms for rails and heavy shapes, or billets for bars and wire rod. Control of flow rates, mold oscillation, secondary cooling, and mold powders minimizes internal defects, segregation, porosity, cracking. For special steels, vacuum arc remelting, VAR, or electroslag remelting, ESR, may be used. Semi-finished products move to rolling. For flat products, slabs are reheated in pusher or walking beam furnaces to 1150 1250°C, and hot-rolled in roughing and finishing stands down to a few millimeters. Hot strip is cooled and coiled. When tighter tolerances, better finish, and higher mechanical properties are needed, hot-rolled coil is pickled and cold-rolled in tandem mills, then annealed, continuous or batch, and if required, skin-passed. For long products, billets and blooms feed hot mills for bars, rounds, wire rod, beams, and rails. Controlled cooling on the runout, accelerated cooling, online normalizing, tunes properties. Heat treatments tailor microstructure and performance. Spheroidizing anneals for cold formable grades, normalizing to refine grain, quench and temper for high strengths, tempered martensite, controlled bainite transformations, trip, twip, strategies for automotive steels, solution annealing and passivation for stainless. Selecting TTT, CCT paths and heating-cooling parameters is critical to avoid distortion and cracking while achieving toughness, hardness, and formability. Surface finishing prepares products for use or downstream steps. Pickling removes scale with acids, HCl, H2SO4, in closed-loop lines. Hot dip galvanizing, HDG, deposits Zein or Zein-Al-Mg coatings for corrosion resistance. Electrogalvanizing gives highly uniform thin coatings, aluminizing, aluci, and tinning serve high-temperature or packaging uses. Coil coating and wet lamination produce pre-painted products. Trivalent chromating and sealers improve adhesion and durability. For longs, shot blasting and protective primers limit oxidation. For tubes, forming, welding, ERW saw, normalizing and hydro-testing complete the line. Quality control is continuous. Spectrometry monitors, chemistry, temperature and oxygen probes track process state, ultrasonics, eddy currents, X-gamma radiography, and magnetic particle tests detect internal and surface defects. Mechanical tests, tension, bend, impact, hardness, metallography, and inclusion ratings verify compliance with EN, ASTM, ISO, and customer specs. Traceability from heat to coil bar is secured by MES systems and laser marking. Plant logistics and sustainability are integral. Blast furnace and coke oven gases fuel furnaces and power units. Granulated blast furnace slag becomes cement additive. Dusts and sludges are recycled via sinter. Process water is treated and recirculated in closed loops. Bag filters and denox systems cut particulates and NOx. In EAFs, scrap and DRI maximize circularity and cut CO2, especially when electricity is low carbon. Hydrogen-based direct reduction, H2DRI, and oxy-fuel hybrid electric furnaces are emerging decarbonization pathways. The transition from semi-finished to finished requires conditioning and tight tolerances. Plates are edge-trimmed, leveled, and cut to size. Coils are slit and cut to length. Sheet receives certifications for flatness, roughness, and coating. Bars are straightened, cut, bundled, and grade stamped. Wire rod is patinated or phosphated according to end use. Drawing, fasteners, ropes. Sections and beams are dimension checked and straight. Rails receive head hardening and ultrasonic testing. Tubes are sized, beveled, tested, and marked. The procedure ends with packing, certification, and shipping. Each lot carries a mill test certificate, heat analysis, mechanical results, treatments, NDT. Packing protects against corrosion and shock. Logistics coordinates rail, road, and sea to supply construction, machinery, automotive, energy, appliances, and shipbuilding. The entire journey, from origin to finished steel, is an integrated sequence of thermochemical and mechanical transformations, governed by real-time controls and circular practices that return scrap and byproducts to the start of the chain, closing the steel loop.